So, dear student, so today we'll be discussing about superconductivity in detail. Okay, so I'll be sharing the screen now. Yes. So, superconductivity. So, we have been hearing this term quite some time. Correct. So, just to tell you what is superconductivity here. So, we got introduction to superconductivity discovery. So, what happened in this is, so it's in the year 1911. So, one of the scientists. Okay, I'll just stop the screen sharing here. So he was studying the mercury, basically, the temperature dependence on mercury. Okay. So mercury, it offers some resistance. Any metal or any non-metal or whatever it is, any alloy or whatever, obviously there is some resistance. Okay. So there is some resistance. So he was detailedly in studying the temperature dependence on mercury. In the sense, how is the resistance flowing through the resistance will only happen when we apply a current, when switch is on, correct? When there is a current flow, then there will be a resistance, correct? Yes or no? Obviously there will be some force to stop the flow of current. That is nothing but the resistance meaning. So what happened is that when the temperature was between 0 and 4.15, when the temperature was between 0 and 4.15, this mercury, okay, this mercury did not show any resistance. In the sense, the current was able to flow through it very peacefully. Okay, I'm telling you in simple words so that you'll understand. So between 0 to 4.15 when the temperature was. But when it is greater than 4.15 or when it is less than 0, then what? Then it showed resistance. But between 0 to 4.15, there is no resistance for the flow of current. So it's a free flow of current. So this is basically called the superconductivity, because after this temperature greater than 4.15 or less than 0, there is a resistance. So when there is no resistance and there is a free flow of current, this property is called superconductivity. So why I told you is because today's full topic is based on this superconductivity. The temperature depends on resistivity and everything. Which yeah, the graph is very important. Yeah. So the temperature which I told you, right, between 0 to 4.15, that is called the critical temperature. Okay, TC we will say. TC, critical temperature. Meissner's effect. So Meissner's effect is basically, if you see the diagram, we will come to know here. When T is greater than TC, when temperature is greater than critical temperature. And second graph is what? When T is less than TC. Correct? So when, I'll just read the first line. So Meissner showed that when a superconducting material is placed in a magnetic field, it allows magnetic flux to pass through it if its temperature is above Tc. So if it is above the critical temperature, what is this lines? Number of lines passing through any surface is called flux. Number of lines passing through any surface is called flux. Okay. So when the temperature is greater than critical temperature, it's allowing what? The flux to pass through the particular material. But when the temperature is less than Tc, is it allowing the flux through to pass through the material? No, it is expelling. It is not allowing it to pass through. So this is basically called what? Meissner's effect. Okay, so if it is expelling, second case, what is happening? T less than Tc, it is expelling. In the sense, it's not allowing the flux to pass through it. In the sense that material will become perfectly diamagnetic in nature. So this is called my Meissner's effect. And this is the expression we have to write. B is equal to mu naught into H plus M, where B is the magnetic field, H is the magnetic field intensity, M is magnetization. Okay. So when superconducting state is there, then B is equal to 0. B is equal to 0. Okay. And when Meissner's effect has to happen, then susceptibility will be equal to -1. So then only it is perfectly diamagnetic in nature. This already is in class 12 also. Critical field and its temperature dependence. Anyway, let's come back to that last. Now coming to my type of superconductors. Soft superconductor. So the name itself, two types are there. One is soft, other is hard. So soft superconductors, we can't use it in real life application because superconductivity, especially for industrial, let's take the magnetic leviating effect or any industrial related things can't be achieved in soft superconductors. Okay, because it cannot withstand very high magnetic field. Okay, but it shows superconductivity, but it cannot exhibit that much magnetic field. In the sense, it's not able to withhold the magnetic flux passing through it. So that is my type 1 superconductor, like my mercury, lead, zinc, and all. This is my type 1. But type 2, it can withstand the high magnetic field and it can withstand high magnetic flux passing through it. Okay, so it's able to fill more flux through that particular material. So its superconductivity is very, very more. So we can see superconducting state, correct? So this much state is there. We can see it. So it is able to lose its diamagnetic property. Okay, so susceptibility is not equal to -1 in this. BCS theory of superconductivity. So Bardeen, Cooper, and Schaefer. Yeah. So according to him, there is a formation of copper pair. So copper pairs are nothing but we know that two electrons, correct? Two electrons basically, if two electrons are comparing, what is happening? Repulsion is happening, correct? But electrons formed by what? Two electrons are coming together, but with opposite spin. With what? Opposite spin. So then we get a pair of copper pairs. And then there is a term called phonon field here. I'll just, yeah, the phonon. See, phonon is nothing but it's an interaction between the microscopic and microscopic materials. It is like the atoms and molecules interaction within that particular metal. So obviously the electrons, two electrons coming with the opposite spin will have a more energy compared to that of the phonon. Okay, fine. Then what it shows? Then it shows that the two electrons, correct? So T less than Tc, the critical temperature. So we'll come back to the Meissner's effect. Meissner's effect is basically what? If the critical, if the T less than Tc, if T is less than Tc, then magnetic flux is expelled. But in this case, T will be greater than Tc. The copper pairs will be able to form much more energy compared to that of the phonon. So T will be greater than Tc respectively. So if T is greater than Tc, then we all know that what the magnetic flux, the flux will be flowing through the particular metal or material. So it exhibits superconductivity. So, and this is our diagram we have to study. Yeah, quantum tunneling, a very simple concept, only the name is difficult again. So we can see the energy of the particle going in a sinusoidal way, and there is a barrier, wall. Barrier means a wall for us, correct? Correct? A potential way. So what happens if, for example, when I'm throwing the ball, let's say a ball is there, and I'm throwing it just like this. Yeah, I'm hitting it the ground and throwing it, and there is a ball. And after some time, what will happen? If the ball will hit the wall and will come back to me, correct? Yes. Suppose if I'm not stopping it, what will happen? Again, it won't follow in that sinusoidal pattern, right? It will settle on the ground. But in quantum tunneling, the concept is before tunneling. This here we can see the E is greater than V. Correct? Energy is greater than the potential energy of the barrier. If the energy of the particle is greater than potential energy of the barrier, okay, so we can see that once it reaches this barrier, then there will be smooth after this thing, no? Yeah, the momentum will slow down and there will be smooth movement of the particle. So this is nothing but the quantum tunneling. That's all. So this exponential will be gradually decreasing. Now coming to the Josephson junction. So we got DC Josephson effect and AC. Both are same. There is no much different. Same thing. What this Josephson is saying is, we have just now discussed what in BCS theory copper pairs. Correct? So this copper pairs will pass through what? The thin insulating layer. So I'll keep it two superconductor. I'll keep it two superconductor. And then what? I'll be keeping an insulator, a very thin insulator. Yeah, separating the two superconductors. Correct? So this superconductor insulator, here I'm keeping air as the insulator. Okay, that is the cheapest insulator available. So between the hands, air is the insulator. So superconductor, insulator, superconductor. This is called Josephson junction. This is called my Josephson junction. Okay. So again, just remember that I told about the mercury experiment in the beginning, right? Between 0 to 4.15 temperature is the critical temperature. We can see what the free flow of current. That free flow of current, yes, between the two separate superconductors separated by a thin insulator. This is called Josephson effect. And the current flowing through that particular insulator between the two superconductors is called what? Josephson current. Now, the important factor of this current is this current will keep on flowing irrespective of no external DC or AC voltage. That's all. You got the point, huh? Yes, fine. But so this current keeps on flowing when there is no external voltage applied. But if I connect an external voltage to this particular free flowing current, then it will form an oscillation and it will shows what? The AC current. In the sense, AC voltage will be formed, AC oscillation will be formed if I put an external DC voltage to this particular free flowing current. So coming to my DC Josephson effect, same thing. Keep two superconductors separated by a thin insulating material. Correct, and the current is formed. Correct, this is a free flowing current formed when when it is between 0 to 4.15 and temperature is. Yes, so that free flowing current is called what? Josephson current. The name of that current is Josephson current. And also this current will continue to flow irrespective of the DC voltage if I apply or not. And if I'm applying the DC voltage, then it's called what? My AC Josephson effect. In the sense, I'll be getting a AC voltage oscillation there. So this is my experiment here. Superconductor, two superconductor, separated by insulation pair, copper pair. That is free flow of electron. That's it. So IS is equal to IC sin phi. IC is nothing but my critical current. Okay. And IS is nothing but my super current through the junction. That's all. So these things you have to study and keep. So theoretically, I told you what is to be written. So that's it. And coming to SCUD. SCUD is nothing but my superconducting quantum interference device. And the main purpose of SCUD is to measure the very weak magnetic field objects. Okay, so we got two types of SCUD. One is DC SCUD and RF SCUD. So DC skewed, obviously, DC Josephson effect, the is applied into this. So obviously the supercurrent will flow through it irrespective of the absence of DC voltage. And RF skewed, obviously one is DC, so other will be AC Josephson effect. So the name itself is very difficult to pronounce. AC Joseph effect, I'll pronounce it as of now. Okay, because Josephson effect and all very difficult. So your AC effect. So yeah, coming to the AC effect or the AC Josephson effect, whatever I discussed with this previous thing, you try the same thing on this also. Finally, the application superconducting quantum computing. So mainly three sided you should write charge qubits, phase qubits, and flux qubits. So in the phase qubits, you should write what? My DC skewed type. Okay, DC skewed type. Flux qubit. What is my flux qubit? I'll show to you what it is. See, we can see charge qubit, phase qubit, and flux qubit. So in flux qubit, there will be an inductor. In phase qubit, there will be a supercurrent always passing through the particular circuit. And charge qubit, there will be a capacitor. And we have something called CPB, the copper pair boxes. So the diagrams are very, very important. So obviously, these are all superconducting reservoir. The sense permanently the flow of current will be passing through it, irrespective of any external voltage. So that's it. Thank you.